Hey, I hope you guys are all doing well. I want to make sure that you guys stay on track to get done with what we need to get done. So I'm going to show you a video lecture of what we need to finish up. It's going to start with a video on the web, so just pay attention to what's going on here, and then I'll add some things to it.
In the 1930s, Linus Pauling introduced the concept of hybridization to explain chemical bond formation. Hybridization is the mixing of atomic orbitals in an atom to generate a set of new atomic orbitals called hybrid orbitals. Click on one of the hybrid orbital buttons to see how hybrid orbitals are produced. Mixing an s orbital with one of the p orbitals generates two equivalent sp hybrid orbitals. Note that the number of hybrid orbitals is equal to the number of atomic orbitals that are hybridized. The set of two sp hybrid orbitals has a linear arrangement. The angle between the orbitals is 180 degrees. Mixing an s orbital with two of the p orbitals generates three equivalent sp2 hybrid orbitals. Note that the number of hybrid orbitals produced is equal to the number of atomic orbitals that are hybridized. The set of three sp2 hybrid orbitals has a trigonal planar arrangement. The angles between the orbitals are 120 degrees. Mixing an s orbital with the three p orbitals generates four equivalent sp3 hybrid orbitals. Note that the number of hybrid orbitals produced is equal to the number of atomic orbitals that are hybridized. Hybrid orbitals has a tetrahedral arrangement. The angles between the orbitals are 109.5 degrees. Mixing an s orbital, three p orbitals, and a d orbital generates five sp3d hybrid orbitals. Note that the number of hybrid orbitals produced is equal to the number of atomic orbitals hybrid orbitals has a trigonal bipyramidal arrangement. The angles between orbitals are 120 degrees in the trigonal plane and 90 degrees between orbitals in the plane and those above and below the plane. Mixing an s orbital, three p orbitals, and two d orbitals generates six equivalent sp3d2 hybrid orbitals. The set of six the number of hybrid orbitals produced is equal to the number of atomic orbitals that are hybridized. The angles between the orbitals are 90 degrees.
Sorry, you guys, that it always seems to mix up there. But essentially what we've got going on is when I hybridize, I mix orbitals of an atom to produce new atomic orbitals that carry the characteristics of each. I always get the same number that I put in, and they always spread out as far as possible in space. So now I want to continue on with our lecture. And what I want you guys to see is how we can apply this to determining the shape of molecules. So essentially with orbital hybridization, if we want to know what it is, for us it's just going to be a way that we can describe how atomic orbitals mix to give equal bonds, because we know S looks like this, P looks like this, and D's look like this. Those are not the same, so if they're going to make equal things that bond in equal directions of equal strength, they have to mix. So how does it happen? We mix orbitals and make them equal energy. So for example, if I take an s orbital here, a p up here, and decide to hybridize these two, then I no longer have an s and a p. It becomes sp, and there are two of them of equal energy. Why does it happen? This allows, like we said at the top, equal bonds to form. And we know this does this. If I have CH4, for example, and I'm going to have C, H, 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 you explain to me how I'm going to get that out of a carbon that has an s orbital and 3 p's. It's not possible. But if I take that carbon and make it be 4 sp3s, we can get that, because I will have this, I will have this, I will have this one, and that one. Now they're all equivalent. Possibilities, you saw them on the video. We can hybridize S and P together to get SP. We can make S and 2 P's and make it SP2. We can pull in S and all 3 P's, make it SP3. We can pull in an extra D with those, so 5 things becomes SP3D. If I need 6, it becomes SP3D2. And those are the only possibilities that we'll see. So how does this relate to molecular shape? Well, VSEPR, or valence shell electron pair repulsion, is going to help us understand this. What causes it is the fact that electrons are negative and repel each other. Duh, that's in the name here, right? Electron pair repulsion. But we're specifically talking about those in the valence shell. So what results from it? Well, we get max separation of electron pairs in 3D, 3 dimensions. So this leads to molecular shape. And how do unshared pairs affect this? Well, unshared pairs stay with one atom. So they squash shared pairs that we call bonds. So they're stretching or squashing the bonds. Think of this as having that brother who's off at college who comes home and he may crash on the couch. He gets a little bit of space, but you have your own room, and so you get all kinds of space. For example, let's take a look at CH4, and I'm going to try to do it justice here in 3 dimensions. This guy's sticking out a little more. These angles are all 109.5. However, if we look at a similar structure, like NH3, for example, who has an extra pair there, essentially this bond gets squashed. It goes from 109 to maybe 108. And over here, this bond between the lone pair or the unshared pair and the bond gets bigger. So maybe it's more like 111 degrees, maybe. And so those unshared pairs push all the other things down. It's kind of like scissors. They squash them down because they require more space. Alright, so we'll start this, and I'll probably have to continue it in another lecture, but essentially we have the following possibilities. I can have 2 total domains. That means I have at least 2 atoms attached to my central atom. If I have 2 total domains, then I can have 2 bonding, 0 non-bonding, and my geometry is linear. So if I have X, A with no lone pairs, that's what I have. The only two things I can do, if I separate two things as far as possible, that is 180 degrees. Example of this is CO2. So we'll redraw our structure for CO2. CO2 has 2 bonding domains, and the carbon has no non-bonding domain. So linear relationship is the best we can get. Alright, I'm going to stop this lecture here and we'll continue with number 2.